This is Principles of Ecosystem Ecology, Chapter 3, Geology, Soils, and Sediments. In the first part of the chapter, the introduction, we learn that within a given climatic regime, soil properties are the major factor governing ecosystem processes. After understanding the climate of an ecosystem, an understanding of the structure and functioning of soils is critical. The authors state that within a given climatic regime, soil properties are the major factor governing ecosystem processes. They also state that soils form a thin film over Earth's surface in which geological and biological processes intersect. Given that, what is soil? Empirically, when we dig holes in different places, soils look really different. So for example, in the tundra, soils look relatively organic. Lots of brown material, often with water or ice at relatively shallow depths. In contrast, when you look at forests in the temperate regions, the soils look a lot different. There's a relatively thin layer of organic material and undecomposed litter. And then below that, you can have relatively deep profiles that have been processed to different degrees. These would have a color that's characteristic of these forests, but different than other places. When we get into subtropical and tropical regions, the soils can look even more different. Here you can see again a relatively thin layer at the top of organic material. And then when you get down below, you'll see a gradation of color to these deep, rich red layers. All of these are soils, and all of these function more or less the same, but differ in really important ways. The Soil Science Society of America defines soils as the unconsolidated mineral or organic material on the immediate surface of the earth that serves as a natural medium for the growth of land plants. That's a definition of soil, but what's the definition of dirt? Well, dirt is just soil out of place. So what is soil made of? Soil is a mixture of solids, liquids, and gases. And often we forget about the liquid or the gaseous part of soils, but they're a mixture of all three, and all three are important in defining the soil and how it functions. In general, solids are about half the volume of soil. But that can vary among soils, especially when the soils become compacted. So for example, in a typical undisturbed soil, again, mineral material and organic material is about half of the soil, and then equal parts of water and air. In a compacted soil, those air spaces become greatly reduced, and it holds a lot less. The air spaces become greatly reduced, and it holds a lot less water. So there, you'll have a much greater mineral component, but a lot less water and air there to support the growth of plants. In general, soil has a few key functions. It provides a source of water and nutrients to plants and microbes, but also air. And that air component is important too, because plant roots themselves, as well as the microbial community, are heterotrophic, and most of them will need oxygen. In addition, that soil serves as a physical support system for plants. So if you go and you dig in a grassland, for example, and excavate the root systems of plants like this Tripsicum here, you'll see the root systems that extend down here. And these roots are going to go out, interact with the soil and the microbial community in the soil, and provide water and also mineral resources for the shoots of the plants. In addition, when we think about soils, not only do we think about plants, but also the decomposer organisms and the animals that live in the soils. So fungi are a critical component of most soils, and they serve a number of functions to decompose and recycle organic material. There's a whole host of other organisms that we'll need to think about, such as different bacteria, nematodes for example, as well as mites. These are generally referred to as mesofauna, and we'll work on those later. Now this chapter is also about sediments, but in general, sediments are a lot less important in lakes than soils are to terrestrial ecosystems. Sediments serve as a repository for mineral and organic material in lakes, but plants in those lakes are a lot less dependent on the sediments than terrestrial plants are on soils. Soils are important because they mediate many key reactions in global elemental cycles. A lot of the time when we're thinking about these key cycles such as nitrogen, phosphorus cycles, most of that occurs in the soil itself. So an understanding of the soil gives us an understanding of these elemental cycles. And these soils provide essential resources to organisms that drive these cycles. Now in Chapter 3, we're going to cover a few main ideas. We're going to think about soil processes that occur over long time scales, and these are going to be important. We're not going to just think about what happens on the short time scales on a daily cycle, but how these soils develop. In addition, soils are strongly influenced by physical and chemical interactions. We're going to think about what some of those key physical and chemical interactions are. And most importantly, we're going to learn the key ways that soils differ as we look at them on a global scale. So both how they function and the commonalities that they have, but also their key differences. Now, the authors offer a focal issue to think about soils and their importance a little bit more. And they state that human activities have massively increased nutrient and sediment inputs from terrestrial to aquatic ecosystems. And here they're going to highlight that not only are soils important when they're in place, but the consequence of losing soils, or for soils to be transferred from one ecosystem to another. At the most extreme, we have situations like the Dust Bowl that happened in the central part of the US. And here's a situation where extensive cultivation had replaced the grasslands, and the practices that they had used had caused massive erosion due to wind. Now, the representative questions that the authors offer as examples of key questions to think about for soils are: what properties of vegetation and soils cause some soils to be more susceptible to erosion than others? If you're to look at a map of erosion, that there would be differences in the amount of erosion that you get in different systems. Some of that is going to be linked to topography, for example, but there are other factors that are important too. The Dust Bowl is really restricted to a relatively small area of the central part of the US. And what was it about that area that caused those soils to be more susceptible to erosion than others? And why are topsoils, which are the first layers to be eroded, so much more fertile than deeper soils? So losing soil material isn't necessarily all bad, but generally it's the top part of the soil profile that's lost first. And this has much greater consequences for the fertility of those sites than if you're to somehow lose deeper soils. And lastly, what management practices sustain the productivity of soils and reduce erosion rates? If for ecosystems we're trying to reduce erosion rates, and it should be said that erosion is a natural part of ecosystems and has been for a long time, but if we're trying to reduce erosion rates, what are the management practices that we would use to do so? And understanding this question and answering this question requires a good fundamental understanding of all the processes and properties of soils that we're going to talk about.